So I'd like to start by thanking the organisers. It's a great pleasure to be back in Cambridge, and it's an even greater pleasure to just say in public that Adrian was my first teacher in set theory, and I think to a large extent he formed my taste, though he might not wish to be held responsible for too much of that. And so when I saw Adrian at the start of this meeting, he said he'd read my abstract and wasn't quite sure what it had to do with Matthias. So, and it's a good question. It's a good question, but you'll see as the talk progresses, there's forcing, there's idiosyncratic filters, there's something with the flavor of Ramsey theory, so I think there is something. Something, I don't know, what's the adjective? Matthias-esque, I guess that's... all right, so I should say, sorry, I guess I owe you a title. So slight change from the program. The talk's now called Dowker and super-Dowker filters. So just to dispel any confusion, this is the same Dowker as in Dowker spaces, but as far as I know, there isn't really any connection between the objects that I'm going to discuss, the Dowker filters, and the Dowker spaces. They come from another problem in topology, which I do not understand too well. I'm sure that there are plenty of people in this room who understand these matters better than me, and I'd be happy to hear from them at the end of the talk. So let's say, I should also say, it represents this is another connection with Adrian actually, represents some joint work with Charles Morgan, who was another contemporary of mine in Cambridge, who Adrian also taught set theory to. Right, so we're going to start off with just some kind of structureless underlying set X, and we're going to have a filter on X, and we're going to be interested in sequences of subsets of X indexed by elements of X, and we'll call those F sequences. So an F sequence is a sequence indexed by elements of X consisting of subsets that are large for X. And for the purposes of thinking about this, it's very helpful to think of this as being just a directed graph on the underlying set X, in which you have a directed edge going from X to Y exactly when Y is a member of A sub X. So in particular, let's say that distinct elements X and Y, let's say they're related if each one is a member of the other one's set. So of course in graph language I'm just saying there's a directed edge both ways. And now in connection with problems in topology, Dowker defined a kind of filter. Naturally he didn't call it a Dowker filter, but Mary Ellen Rudin later dubbed these things Dowker filters. So the definition, certainly due to Dowker, though he didn't call them Dowker filters, but I'll say F is Dowker if and only if. So there are going to be two properties, and part of the point, there's some kind of tension between these two properties that we would like the filter to have. The first one, we'd like to say for every F sequence A, there exists related points. So I'd like to say whenever you've got a sequence of large sets, you're going to see these arrows going both ways. And this is already telling you something about what F could possibly be like. For example, if F lives on some ordered set, and concentrates on tails, then it certainly does not have property 1. Okay, so but property 2 is saying you don't have property 1 for too trivial of a reason. So this one says for every partition of x into 2 pieces, x0 and x1, there is an f sequence such that you do not see a related pair where one vertex, if you like, is drawn from one side of the partition and the other vertex is drawn from the other side of the partition. So we're saying, given any partition, I can find one of these directed graphs in which, whenever you have a related pair, either it's drawn from one side of the partition or the other. No, I mean directed because there's an there's an edge from x to y if y is in a sub x, and that's not the same as x is in a sub y.
Is x allowed to be in a sub x?
Yes, it's okay to have loops. That's completely fine, but actually completely irrelevant for.
X belongs to AY and Y belongs to AX.
Hmm?
That's the definition.
That's the definition. That's the definition. No. Yeah. Okay. All right. Okay. So I should say that I think since time is possibly tight, maybe I'll just say this. So in 1984, Mary Ellen Rudin constructed in ZFC a kind of related structure. So what Rudin constructed was a set with a family of filters. So each point in the set gets its own filter. And with that variation, she was able to construct things that satisfy the appropriate versions of these axioms. And that enabled her, and I haven't read this paper carefully yet, so please don't ask about it, that enabled her to construct a simplicial complex, which I think is normal and not collection-wise Hausdorff, which was at least, I think, close to the problem which had led Dowker to think about the Dowker filters. Okay, because one of the strange things about this historically is that whether it was even consistent that there should exist a Dowker filter was open for a long time. Okay, and in particular, when Mary Ellen Rudin did this construction, it wasn't clear that it was even consistent that there's a Dowker filter. All right. Also, again, historically, I understand from reading a very nice survey paper by, I want to say, Gary Grunhager, and another author I'm blanking on, that actually this result of Mary Ellen Rudin's had some influence on Balog's construction of a small Dowker space. But so there is some marginal connection with Dowker spaces. Anyway, so before going any further into the guts of this, here are some things. Dowker didn't know whether Dowker filters existed, but Dowker did prove that they've got to be kind of peculiar if they do exist. So LF0, so if F is a Dowker filter, then just on, say, X. If F is a Dowker filter on X, LF0 is less than the minimum size of an F, strictly less than the minimum size of an F positive set, which in turn is strictly less than the minimum size of a set in the filter. So they're kind of peculiar, and they're very far from being ultrafilters. So the positive sets really have kind of a different look from the large sets for these filters. Okay, so then in about, I want to say, 1991, Balog and Grunhager actually gave the first consistency proof in ZFC. We'll see why I'm stressing ZFC. Mellon and Grunhege gave a consistency proof for the existence of a Dowker filter by iterated forcing, and what they did, they say V believes GCH and kappa's uncountable, kappa's regular, not the successor of a singular cardinal. So kappa's obviously either the successor of a regular or inaccessible. Then they produced, so then in a kappa closed, kappa plus CC iteration, so iterated forcing extension, what you get is that 2 to the kappa is kappa double plus, and there is a Dowker filter on kappa plus. So I think, again, for reasons of time, I don't want to really get into the details of this. Once you have a Dowker
filter on
kappa plus.
kappa plus, not kappa double plus.
No, on kappa plus. So the point is, it'll be natural. You'll see why that's natural in a second. The point would be, you have kind of kappa double plus many issues in the form of partitions. And for each one, you'll want to be generically adding a witness to property 2. So you seem to need the kappa double plus. In fact, I should say, this is a case of giving a talk about the problem that you could solve rather than the problem that you wanted to solve. So as far as I know, it's still open whether Dowker filters actually just exist in ZFC, whether there's any construction on any cardinal of a Dowker filter in ZFC.
How about LF2? That's the smallest part.
Yes. So certainly, LF2. So certainly you can build the Balog-Grunhege thing and get one on LF2.
Yeah.
Consistent, but no, actually, no, not known. Not known. Also, something I should say, if you have a Dowker filter on X, you can make a kind of trivial Dowker filter on a larger set just by kind of blowing it up. But this is a properly Dowker filter. This is going to be a Dowker filter on kappa plus, which actually wasn't obtained from a filter on a smaller cardinal by blowing it up. All right, so let's go back in time a second. So the Balog and Grunhege theorem is from the early 90s, but in the late 80s, it was published in 1988. There's a paper in the JSL by Chris Freiling and Payne, where falling back from ZFC to ZF, they did actually prove some relevant results. But before I can state the relevant result, I need a definition. So let me introduce another property, 2 star. No, I'll call it 2 plus. Okay, plus is obviously super. All right, so 2 plus is a strengthening of 2. Same setting, you have a filter F on a set X. 2 plus says that for every partition of X, it says there is an F sequence, there is an I, such that all related pairs lie in Xi. So it's a strengthening of the game. And now my kind of oracular remark that there was something Ramsey-like about this whole story maybe now makes a bit more sense. So a filter F is super-Dowker if F, still I want property 1, but now instead of 2, I'm increasing the game and I want 2 plus. Okay, so it turns out that, it wasn't obvious to me, but I was telling my colleague Clinton Connolly about this, and he said, oh, that's obvious. So it turns out if you are in the right kind of model of ZF, you can actually get super-Dowker filters. The downside is you're going to get it on a set which is rather far from being well orderable, I think, in that kind of model. So Frieding and Payne materialize things. So, one, if you have ZF plus all sets of reals have the property of Baer, so certainly a consistent assumption, not an outrageous assumption. If you have ZF plus every set of reals has the property of Baer, then there is a super-Dowker filter, but I think it's on some, the underlying set is some quotient by some equivalence relation of sets that are a couple of power sets up, so it's not a tremendously simple thing. All right, now more relevantly, okay, this is the last time in the whole talk that we're going to be working in any theory weaker than, well, any theory other than ZFC or ZFC plus large cardinals. So in ZFC, Frieding and Payne made some observations. So I guess the first one might not need ZFC. If F is still Dowker and Payne, if F is super-Dowker, then there's a natural ultrafilter associated with F, namely the ultrafilter which tells you which side of the partition is going to win. So we say F twiddle is the collection of A contained in X. There is an F sequence such that all related pairs are drawn from A. Well, then actually, this is an ultrafilter containing F. Okay, it's easy to see that it contains F because if you have, yeah, it's easy. It's an exercise in 1 and 2. All right, so what? So also they showed that, so then use an ultrafilter, use countably completes, use non-principal. Okay, so from the ZFC person's point of view, we're now obviously in the world of large cardinals because the additivity of this filter is going to be a measurable cardinal. So in particular, you're not going to see the Dowker filter existing anywhere below the first measurable cardinal. All right, so with these preliminaries, I'm coming to that. Okay, so because I don't know the answer, but something about the things that I do know is quite suggestive about what might be true. All right, so there's a theorem. I said it represents joint work with Charles Morgan. So we can actually do a couple of things relevant to this. So for the first bit, the hypothesis is just that if kappa that's all we need. So we want kappa to be uncountable, and we want kappa equals kappa to the less than kappa. Then, so in the extension, I add kappa double plus. So there is a Dowker filter on kappa plus. And again, it genuinely does live on kappa plus. It's not made from any smaller filter by trivially blowing it up. Okay, and this is, I think, somewhat germane to Ishvan's question. If V, I'm saying this rather cagily, so I want to say if V is Lever's model in which kappa is indestructibly supercompact, then actually, in the same extension, again, in the extension by add kappa double plus, there is actually a super-Dowker filter. Super-Dowker filter on kappa plus. And even more suggestively, remember, whenever you have a super-Dowker filter, you have this thing that I was calling f-twiddle. So in the model in which one gets the super-Dowker filter on kappa plus, the filter f-twiddle is the most natural kappa complete uniform ultrafilter on kappa plus in this kind of universe. And somehow it's not clear to me at this point that just kappa being indestructibly supercompact or being supercompact in the add extension is enough to get this to go, because the point will be, to make the construction go, one needs a certain master condition argument, and so maybe one needs to have done really the Lever preparation to make it go. Aki, how am I for time at this point? 37 minutes. Okay. Okay. Very good. All right. So.
Sorry, James, just can I bring you back to that word U? What was the conclusion about this U?
Oh.
U equals to F.
Oh, I'm sorry. U is f-twiddle. Sorry. Sorry. F-twiddle is an ultrafilter. F-twiddle is countably complete. F-twiddle is non-principal. Okay. Let's see. Where was I? Right. So the question is, how are we going to do this? So the idea, I should say, is due to Charles. The idea is we are just going to use the generic sets which are added by this co-enforcing, and then we're going to tweak them a little bit and allow them to generate a filter and argue that it works. So so it's kind of the opposite approach to the Balog and Grunhager paper. So there they do an iteration. As the iteration progresses, you see more and more partitions of kappa plus. They add sets that are intended to do the witnessing job, and but this is kind of a shortcut to the same goal. So let's let G be add kappa double plus generic. So in particular, you probably think of the generic object some way or another. For the purposes of this talk, the way to think of the generic object is that it's a kappa double plus sequence of subsets of kappa plus times kappa plus. So that's how I'm going to view the generic. So I'm going to identify, just by identifying kappa double plus with the Cartesian product kappa double plus times kappa plus times kappa plus. So I'm going to identify G with a sequence of sets, let's call them AI, I less than kappa double plus, AI is contained in kappa plus times kappa plus, And then I'm going to further identify this guy here, this kind of kappa plus times kappa plus matrix of zeros and ones. I'm just going to think of it as AI. So I'm just going to look at it, I always get confused. I'm going to look at it row by row, and looking at it row by row, I'm going to see a sequence of kappa plus many subsets of kappa plus. All right. So now, also what we're going to have, the other player, if you like, in VG, I'm going to enumerate the partitions of kappa plus. It's better to think of them as functions now. So these are going to be functions from kappa plus to 2, EI. So the partition, if you like, is just the partition into the preimage of 0 and the preimage of 1. Okay. So the idea is we would like the ith block, we would like this sequence here of subsets of kappa plus to do the job of witnessing property 2 for the ith partition in this sequence of partitions. But the problem is, of course, that it probably doesn't. Right? There's no particular reason to think that, whatever generic set the construction actually gave us at coordinate I, whatever, generic sets and sequences identified in this way, whatever the construction gives us, it probably doesn't do the job for the partition E sub I. And then we just take a robust approach and modify it till it does do the job. So, I think for, I don't even know if I'm going to get that far. With an I to the super-Dowker proof, it actually matters a little bit how I do the modification. So, how am I going to modify? I'm going to say, so, alpha less than beta. Let's say that's bad. So, here I is less than kappa double plus. All right, let's look at the places where things might go bad. If we try to use the AI betas for beta less than kappa plus as a witness to property 2, remember I'm just doing Dowker filters right now. I should say I'm not yet doing super-Dowker filters, but for it to be a problem for Dowkerness, well, we have to see a certain configuration. So what's the bad configuration? If alpha shows up in beta's set and beta shows up in alpha's set, and EI of alpha is not the same as EI of beta, that's the bad configuration. So then what we do is we want to replace, if you like, one of these ones by a 0. So what we're going to do is we're going to say we're going to remove the pair alpha beta from AI. Okay. So you should think of this as a kind of selective thinning out of the matrix of sets.
You mean you put them on the one side?
Yeah, what I mean is, so if you want to think of it instead of sets, if you want to think of this thing here as a matrix of zeros and ones, then what I'm doing, before I was seeing a 1 at the coordinate alpha beta, I'm going to strike out that 1 and replace it by 0. Everything else I leave alone. Alright, so this is going to get us, I'm going to call it ADI beta. These are going to be the resulting matrices and sequences. So they're subsets, right? They're subsets of what we had before, obtained by selectively striking out certain points. Okay. here's a lemma, and if you remember what I said before, about the strange business of the least size of a positive set versus the least size of a measure 1 set, this lemma should be quite comforting. So this lemma is going to say, okay, so in V, suppose we have a subset of kappa plus of size kappa, and suppose we also have a set X is going to be subset of kappa double plus times kappa plus of size less than kappa. So then, in Vg, what's going to happen? H is going to meet the intersection over all I beta in X of the altered sets A, D, I beta. So, in particular, I should, let me see.
Non-empty then?
It should be, yes. Thank you very much. Is non-empty. Thank you. So what's going to happen? Let me before I go any further. Let me just say, this is taken straight from what Baylor and Grunhager did with the iterated forcing construction. We're going to let F is the filter generated by all of these altered sets. We're just going to take all of them. F kappa is going to be the kappa complete filter generated by the collection of A beta I as before, together with the final segments of kappa plus. So, and the point is, it should be pretty clear from the lemma that F kappa actually makes sense. But it also is pretty clear from the lemma that F is going to have positive sets of size kappa, like any set of size kappa from the grand model. However, the technical points, F kappa is kappa complete. That's good news. F kappa, the positive sets in F kappa are unbounded because I explicitly threw tails of kappa plus into the filter F kappa. So kind of that's the point, or that's part of the point. And I should say, it's rather important now, suddenly it's rather important that kappa is uncountable, because that means this filter here is going to be countably complete. And countable completeness in some combinatorics that I won't have time to talk about, countable completeness somehow is played off against the finiteness of sets that are involved in generating this filter F. Okay. So now, what's to do? Oh, I should prove the lemma. Okay. I'm sure Adrian must have taught me that proof by picture is bad and to be avoided. So of course I'm going to do proof by picture, so just to prove independence from my advisor. So we're going to have a condition, so proof of lemma, P is an add condition. I've got my H, I've got my X. Well, what am I trying to do? I'm trying to find some alpha in H, which I can force into all these sets. Well, fortunately, H has size kappa, and everything else in sight has size less than kappa. So I'm just going to choose alpha in H, not mentioned in X or P, and now I'm going to extend P to forces in. So I've got a list of tasks. This is where I really hope I can find my notes in a way that perhaps I can't. Okay, so I've got a list of tasks which I must satisfy. Namely, I have to deal with each I and each beta. I drew my picture too small. All right, so let me, again, not drawn to scale. So what's going on here? We're at a particular coordinate, I, less than kappa double plus, and now I've got some relevant betas. Right? I've got some betas such that I beta appears in X, but only fewer than kappa many. So here's 2, that's fewer than kappa. Okay, beta 0 and beta 1, so beta 0, beta 1, beta 1, beta 0. And again, alpha doesn't really need to be here, but it doesn't actually matter. So now what I'm going to do is I'm going to write zeros and ones. So I'm going to write ones here, and I'm going to write, I really hope I have this the right way around, zeros. Now that doesn't seem right. Probably the other way around. 1, 1, 0, 0. Yeah, that seems more like it. So what is the point? So the point is, certainly I'm forcing here that alpha gets into the original generic sets, AI beta 0 and AI beta 1, but I'm also forcing, I just don't care what the partition is saying on this coordinate, because if you look at the definition of badness, the definition of badness only kicks in when the original generic set has an edge going both ways. And here I'm forcing that we only have an edge going one way. So for this, this is the easy bit, and the partition EI is actually irrelevant to the success of this. I'm going to have to speed up. All right, so again, but fortunately I think I learned from Adrian how to lecture fast when under time pressure, so I'm going to say.
Well, some other point from you, you're gonna slow down. So we can follow you.
Okay, well, I was going to say, it was a noble tradition in Cambridge logic when I was a student that you finished on time, so you could go down the pub to discuss the talk that had just happened. So I promised to bring the talk in on time and under budget. Right, so let me just try and say something about how we prove that the filter F does its job. Okay. So what is doing its job? Well, doing its job is having property 1 and property 2. And we've certainly got property 2 because we constructed the filter to enforce property 2. So the point is, of course, to force that we've got property 1. So we'll say, suppose we have, you should think of this as a description of, think of this as a description of basic sets in the filter that will be intersected to give you large sets for which you want to establish property 1. Okay, the filter is generated by, so that this is like a coded description of a sequence of large sets for the filter which happen to have the special form intersection of the basic sets. Okay, so now what are we going to do? So let's let, in fact, if X is contained in kappa double plus times kappa plus, just let A dx equal the intersection over I beta in X of A d I beta. So these are going to be, so in this sequence at alpha, what you're going to see is the set A super D sub F alpha. All right, so now here is where I'm going to cheat you. So in the biggest possible way, right at the heart of the construction. Some ingenious combinatorial arguments from the Balog and Grunhager paper are now going to come into play, and a surprising amount of the argument is going to take place in the extension Vg before we fall back to V. So there are kind of soft general facts about sequences of sets which are members of filters, which we're going to deploy along with the usual delta system tricks. So I'm going to try and give the flavor of the argument, but I can't really give more than a flavor. So we're going to construct H1 contains in kappa plus unbounded, and we're going to construct P alpha in. There would be an H0 if I had more time, but there's not enough time. So P alpha in H1. P alpha is going to say force that F dot of alpha is equal to some definite finite set X alpha plus technical conditions. Okay, so this is the point at which I'm really cheating you. I'm really going to say very little about what the technical conditions are. But if I have time, you will see what kind of thing I'm likely to need to make everything go. All right, so now, after, and by thinning out, we're going to assume, we're going to make repeated appeals to the delta system lemma, which is why I wanted kappa to be less than kappa, equals kappa. So after repeated appeals to the delta system lemma, we can assume that the P alphas are very nicely organized and that the X alphas are very nicely organized. And we're going to choose then alpha and beta. So we're somehow going to choose alpha and beta. And you should think of alpha as associated with P alpha. There's going to be another condition, Q. Okay, but Q actually has nothing to do with P beta somehow. Q is actually going to be associated with some other auxiliary ordinal alpha 0 down here. That's kind of a detail. But the point is, P alpha is going to force desirable things about alpha, and Q is going to force desirable things about beta, and they're going to be compatible. So, in particular, Q is going to decide what is the value of F beta. It's going to decide it as some y, completely unrelated to the original X beta. And the way that things have been organized, and here you'll see that we're kind of in the territory of the delta system. They're going to be, here are some auxiliary sets, delta 0 and delta 1. Delta 0 is, of course, going to be the root of some delta system living on kappa double plus, and delta 1 is going to be the root of some delta system living on kappa plus. And when I said that we've already done a lot of the work, it is going to turn out that what am I trying to say? It's going to turn out that P alpha is already going to take care. So P alpha is going to force alpha in A, D, I beta for, well, let me, yeah, I beta for I gamma, sorry. I gamma for relevant I gamma in delta 0 times delta 1, and similarly Q is going to force beta in AD J delta for relevant J delta in delta 0 times delta 1. So this is kind of getting towards the technical heart of the thing, that we're already somehow going to have taken cares of coordinates that are living inside the root of the delta system. And that's going to give us a very desirable amount of elbow room, because what's the goal? Well, P alpha is compatible with Q. We want to extend the union of P alpha and Q to some R, which takes care of the other coordinates, the coordinates which lie outside. And then the technical conditions, which I'm suppressing, the technical conditions are enabling us to keep everything separated enough that we can extend P alpha union Q in the way that we like. So again, because time is short, and because I at least want to mumble something about the super-Dowker theorem, let me just say one thing. So, idea, we're going to extend P alpha union Q to R to take care of business outside delta 0 times delta 1. So there are coordinates inside, coordinates outside. The coordinates that are outside delta 0 times delta 1 and are relevant for alpha don't have much to do with the coordinates outside delta 0 times delta 1 that are relevant for beta. So we're going to extend R by writing, finitely many more zeros and finitely many more ones. It's going to turn out everything's pretty easy except for the pair alpha beta itself. So by the same kind of tricks that I was using over here, we can take care of all but finitely, there's a certain fixed finite set of coordinates where alpha and beta might go bad. So the key point is going to be on finite set where finite set of I where alpha beta might look bad, we arrange that P alpha union Q actually forces that alpha and beta lie on the same side. So there's some, and I'm saying that just because it's going to have some bearing on the super-Dowker. Okay, how many more minutes am I permitted?
13.
Okay, not bad. All right. So now, let me just remind you. I think I did not learn Blackboard management for engineering, apparently. So let me just remind you what the difference is between a Dowker filter and a super-Dowker filter. Well, the difference is that in super-Dowker, we have a more stringent version of condition 2. And the stringent version of condition 2 says, well, no, it's not just that I want related points to not cross from one side of the partition to the other. I want a fixed side of the partition such that all the related points live on that side. Okay, so here's where the large cardinals come in. So remember, what was my hypothesis for the super-Dowker bit? The hypothesis was we're living in Lever's universe where the supercompactness of kappa is indestructible under kappa-directed closed forcing. So if you know that model well, you'll know that the reason that model works as it does is because in any kappa-directed closed forcing extension, there's an abundance of generic supercompact elementary embeddings added by arbitrarily closed forcing. And that's just the nature of the model. And we're going to use that. We're going to use the some generic freedom that exists in Labor's construction. So what we're going to do is, well, as before, G is add kappa, kappa double plus, generic, as before. We have these sets A, I, beta. As before, we're going to modify them. But now, the nature of condition 2 plus means I should modify them a different way. So now we're going to say alpha beta is bad if alpha's joined to beta, beta's joined to alpha. Let me just say it this way. Okay, it's bad. It's bad unless both alpha and beta lie on the one side of the partition. Okay, so alpha's less than beta. So as before, in this case, I'm going to remove bad has alpha beta from AI, and I'm going to get something, let me call it a SD for super-Dowker sub I. All right, and now what I'm going to do, and I think, again, time limitations mean I'm going to have to wave my hands even more than usual. Now what I'm going to do, I'm going to go to the extension of the Laver model by the add forcing, add kappa, kappa double plus, and I'm going to get an elementary embedding such that the stretched version of the sequence of these A's by the elementary embedding has a particular appearance. So idea in VG, there's going to be a generic supercompactness embedding J from VG to, if you like, H, added by highly closed forcing. If you know the Laver construction, it can really be as closed as you want. Added by highly closed forcing, such that if I look at J of the sequence of A's, then something rather special is happening at each coordinate in the range of J. And what's going to be happening at coordinates in the range of J is I'm going to be working below a master condition, which is going to make sure that certain things happen. So remember, this is the pointwise image of kappa plus. Let's let eta be the sup of the pointwise image of kappa plus. So eta's out here. So the weakest possible master condition would just be the union of the images of chunks of AI under J. And that would be some kind of matrix of zeros and ones living inside this rectangle with indices each in the pointwise image of kappa plus. That's not the master condition I'm going to use. I'm going to use a slightly stronger master condition that says more. I'm going to make sure to have ones along there and zeros along the top. Okay, so what's the point? The point is that now in VG there's a natural uniform kappa complete ultrafilter on kappa plus. So we arranged, this is the point, we arranged in VG if U is equal to the collection of A contained in kappa plus, such that eta, I remind you that's the sup of the pointwise image of kappa plus, is in J of A, then actually all of all of the altered sets are actually measure 1 for u. So, well, this takes a little bit of work. You just have to go back to the way that I did the altering. And the point is, I've arranged that when I do the altering, I don't knock a pair eta j gamma out. Okay, so that's basically all I'm doing from this kind of chapter of large cardinal forcing. Aki, how many minutes? 4. Okay, outstanding. All right, so I think in professional basketball there's a thing called running down the clock, where you want to just play with the ball until the final whistle goes. So, okay, running down the clock. What's going on here? Well, what we're going to do is we're now going to generate f using, I'm not going to use everything. E less than capital plus, I is less than capital L plus. So after the fact, still in VG, I'm only going to use, as my generators, I'm only going to use those elements, those indices I, corresponding to partitions where the 1 showed up on the large side. Okay. And so now, if you think about it, in the light of my kind of heuristic that I want f twiddle to be u, this is like a reasonable thing to do. But okay, so, and also in the light of the way that I did the alteration, remember, the way that I did the alteration was exactly intended to make sure that related pairs ended up on the one side. All right, so now go through the whole construction again. Of course, that's a little dishonest since we didn't really do the whole construction. It's almost word for word the way that it was before until we get to the end game. Once again, at the end game, there is really no problem amalgamating the P alpha and the Q, except that maybe the pair alpha beta itself could look bad at some coordinates. Now, the pair alpha beta can only look bad at a certain finite set of coordinates that was decided early in the construction. So this time, arrange, we use the fact that everything in sight, all of these creatures and all of these creatures are measure 1 for this highly complete ultrafilter to do a bit better. So this time we arrange P alpha union Q forces EI alpha equals EI beta equals 1. This is the key for all dangerous I. Okay, so that seems like a good place to stop, so let me stop.